Hello, everyone. Welcome to today's session on dynamic programming. We're diving into the word wrap problem, a classic challenge often used in text editors to format text within a given line width. We'll solve it using dynamic programming to minimize the messiness of the layout, and I'll provide a short, understandable pseudocode to make the solution crystal clear. Let's get started step by step. The word wrap problem involves formatting a sequence of words into lines, where each line has a maximum width, max width. We're given an array of words, for example, this is a test. The length of each word, for example, 4, 2, 1, 4. A maximum line width max width, for example, 6. Our goal is to arrange the words into lines such that each line contains one or more words, separated by a single space. The total width of a line, sum of word lengths plus spaces, must not exceed max width. We minimize the messiness, defined as the sum of the squares of unused spaces at the end of each line, except the last line, which has no penalty. For example, with words this is a test, lengths 4, 2, 1, 4, and max width equals 6. One arrangement. Line 1. This, width equals 4, and used equals 6 minus 4 equals 2. Cost equals 2 squared equals 4. Line 2 is a width equals 2 plus 1 equals 4, and used equals 2, cost equals 4. Line 3. Test, last line, cost equals 0. Total cost equals 4 plus 0 equals 8. We need to find the arrangement with the minimum total cost. Let's explore some approaches to solve this problem. Brute force, recursive approach. We can try all possible ways to place words into lines, deciding for each word whether to add it to the current line or start a new line. This leads to overlapping subproblems, with a time complexity of 2 to the power n, where n is the number of words, too slow for large inputs. Greedy approach and why it fails. Fill each line with as many words as possible without exceeding max width, then move to the next line. Greedy arrangement. Line 1. Big, width equals 3, and used equals 7 minus 3 equals 4, cost equals 4 squared equals 16. Line 2. Dog, width equals 3, and used equals 7 minus 3 equals 4, cost equals 4 squared equals 16. Line 3. Only, width equals 4, and used equals 7 minus 4 equals 3, cost equals 3 squared equals 9. Line 4. Test, last line, cost equals 0. Total cost, 16 plus 9 plus 0 equals 41. Why greedy fails? The greedy approach maximizes the number of words per line locally, but the squared cost and used space squared penalizes larger gaps heavily. Here, placing each word on its own line, except the last, results in large and used spaces, 4, 4, 3, leading to high costs, 16, 16, 9. It misses opportunities to combine words on a line to reduce and used space, which would lower the squared cost. Dynamic programming, optimal approach. Use dynamic programming to consider all possible ways to group words into lines, minimizing the total cost by evaluating subproblems and choosing splits that reduce the squared and used space. Optimal DP arrangement. Line 1. Big dog, width equals 3 plus 1 plus 3 equals 7, and used equals 7 minus 7 equals 0, cost equals 0 squared equals 0. Line 2. Only, width equals 4, and used equals 7 minus 4 equals 3, cost equals 3 squared equals 9. Line 3. Test, last line, cost equals 0. Total cost, 0 plus 9 plus 0 equals 9. Why DP wins? By considering all possible splits, DP finds that combining big and dog into one line uses the full width, 7, resulting in 0 in used space and a cost of 0 for that line. The remaining words are arranged to keep and used spaces small, 3 for only, minimizing the squared cost. The total cost of 9 is significantly lower than the greedy approach's 41. Let's build intuition for the dynamic programming solution. The word wrap problem has optimal substructure and overlapping subproblems, making DP a perfect fit. Imagine we've processed the first I words, words 0, to words I minus 1. We define memoized array, I, as the minimum cost to arrange these I words into lines, where the last line ends with words I minus 1. To compute memoized array, I, we decide where the last line starts. Try placing words from index j to I minus 1 in the last line, j less than or equal to I minus 1. Check if these words fit, total width less than or equal to max width. Compute the cost of this line, max width minus width, squared if it's not the last line, I less than n, or 0 if it's the last line, I equals n. Total cost equals memoized array j plus cost of this line. Take the minimum over all valid j. Base case, memoized array 0 equals 0, no words, no cost. We'll iterate through each I and try different j values to find the minimum cost. Welcome to the word wrap demonstration. We have 4 words. This is a test and a maximum line width of 6. We will build a memoized array where memoized array I represents the minimum messiness for arranging the first I words. We start with memoized array 0 equals 0 because if there are no words, there is no cost. The array initially looks like memoized array equals 0, dash, 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 dash. When I equals 1, we only have the word this with length 4. We place this on a single line. That leaves 2 unused spaces, so the cost is 2 squared, which is 4. Adding that to memoized array 0, which is 0, gives memoized array 1 equals 4. Now the array is 0, 4, dash, dash, dash. Next we compute memoized array 2, which covers the words .this is. First we try placing is alone on the last line. The word is has length 2, so it leaves 4 unused spaces for a cost of 16. Adding that to memoized array 1, which is 4, gives 20. We also check if we can put .this is on one line, but that combined length is 7, which is too long, so it does not fit. Therefore, memoized array 2 equals 20. Now the array is 0, 4, 20, dash, dash. When I equals 3, we handle the words. This is A. We try 3 options in order. First, we put A alone on the last line. That leaves 5 unused spaces for a cost of 25 plus memoized array 2, which is 20, giving 45. Next, we put is A on the last line. That phrase has length 4, leaving 2 unused spaces for a cost of 4 plus memoized array 1, which is 4, giving 8. Finally, we check if this is A fits on one line, but the length is 9, which is too long, so it fails. Among the valid options 45 and 8, the smaller is 8, so memoized array 3 equals 8. Now the array is 0, 4, 20, 8, dash. Finally, we compute memoized array 4 for the full phrase this is a test. We try putting test alone on the last line. The word test has length 4, but because it is the last line, we assign 0 cost. Adding memoized array 3, which is 8, gives 8. Next, we try putting a test on the last line. That combination has length 6 exactly, so no unused spaces and 0 cost plus memoized array 2, which is 20, gives 20. We also check if is a test fits on one line, but the length is 9, which is too long, so it does not fit. Among the valid options 8 and 20, the smaller is 8, so memoized array 4 equals 8. The final memoized array is 0, 4, 20, 8, 8. The minimum total messiness for wrapping. This is a test. Within width 6 is memoized array 4 equals 8. One way to achieve that is line 1 width. This, for a cost of 4, line 2 width, is A, for a cost of 4, and line 3 width. Test, for 0 cost. The total cost is 8. This completes the word wrap demonstration. Let's see the pseudocode. Memoized array I equals min cost to arrange first I words. For each ending position I, try last line from words j to words I minus 1. For j from I minus 1 down to 0. Add word length and space, if not first word. If line fits, compute cost. This pseudocode computes the minimum cost by trying different starting points for the last line, calculates the line's width, and updates the memoized array with the minimum cost found. Discussing time and space complexity. Time complexity, outer loop, and iterations. Inner loop, up to I iterations per I. Total iterations equals 1 plus 2 plus to plus n equals n times n plus 1, divided by 2 equals O, n squared. Operations inside are O, 1, so overall O, n squared. Space complexity, memoized array of size n plus 1, so O n. That's it for the word wrap problem. We've used dynamic programming to solve the problem, understood why greedy fails, and discussed the optimal solution. Thanks for learning with me today.